Way off. Way off. Way off.
Hear me. All right. I'll begin with a word of prayer. Let me begin. I'll start. I'll try to start. I'm going to start. Dear Heavenly Father, thank you for this day again. I thank you for this time we have to study your creation. Help us to glorify you what we do. And pray for Dr. Scobortis to get back for the next class. Lord, in my prayer, Lord Jesus. Amen. All right. So I think I'm going to talk to you guys about the vector space of n by n matrices. Right? So like n by n matrices forms a vector space, right? So what would be a formula for the length of a matrix? Do you guys know? How would you define the length of a matrix if you were going to? And actually, I could even make this m by n if I wanted to. What'd you say? It's the what? What's the dot product of a matrix, though? Yeah.
So if you do the transpose matrix times the matrix?
That'd still be a matrix, though. How about this? A11 squared plus A12 squared plus dot 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 AMN squared. Would that seem like a reasonable definition for the length of a matrix? Basically, just think of the matrix as a big vector and just string it out and calculate the length of that in Euclidean sense. Interestingly, there is a slick formula for this, which is, it's the square root of the trace of AA transpose. Right? And in fact, if I remember right, you can define this here, AB, is the trace. Now, I could be wrong about this. I'm a little rusty, guys. Would that make sense? What's the trace? Oh, sadness. So the trace of a matrix is the sum of the diagonals. So like the trace of M is equal to like M11 plus M22 plus MKK if M is a K by K matrix. All right. So let me work the formula out here. So does this, first of all, does this even make sense? If A and B are both m by n, we've got what? Like an m by n times a what? An n by m, right? So at least this matrix product makes sense. The formula for the trace in terms of summation notation is this. It's the sum. Let's say I equals 1 to apparently m of AB transpose II. There you go. That's the formula for the trace. And how do we multiply matrices? Like, what's the formula in terms of summation notation for the product of two matrices, the ith component? Well, that is the sum I equals 1 to m, the sum k equals 1 to, let's see, a times b. So we have an n, k equals 1 to n here. And then we've got aik, b transpose ki. What is that? So we got some I equals 1 to m, some k equals 1 to n. What is the kith component of the transpose? How do you do that? What's the definition of transpose in index notation? Do you guys know? Surely you know. This is what? BIK. So we've got AIK, BIK. Does that make sense? I mean, this is the natural inner product of two matrices. You just add together the product of the matching components over all the components. That's the inner product of two matrices. The cool thing is, it even makes sense when they're rectangular. You know, I might kind of expect this only to work when they're square, but it's not the case. It works when they're rectangular. And I just use the phrase inner product here as if that's meaningful. Is it? Is this an inner product? What does it take for it to be an inner product? What do we need? We need linear in the first slot, linear in the second slot, symmetric, since this is a real inner product space, right? And positive definite, I guess, right? Does it have all that? It certainly does, right? Like, why is it symmetric? Check this out. So the trace, well, I guess that's the trouble is you guys haven't done stuff with trace. But a property of the trace is this: the trace of a product is the trace of the product in the opposite order. Like this is something you can prove about trace. And so this is a known identity for trace, and that says that our inner product is symmetric. The positive definite is pretty obvious from the formula, right? If you put AA here, you get a sum of squares. Sum of squares is only 0 if all the squares are 0, right? That's the positive definite. Essentially, the proof that this is an inner product is the same as the proof of the dot product being an inner product, because it's essentially just what? It's just the dot product for the matrix strung out. What's this formula up here? So have you guys talked about for an arbitrary inner product space you can derive a norm? You know this? No? Yes? So like given, if you have a vector space paired with an inner product, so this is an inner product space, we can induce a norm How do we do it? Yeah, so the inner product of the norm of x is equal to the square root of the inner product with x and x. But just what Jeff said, like another way to look at this formula is for this particular instance, the length of the matrix is the square root of the inner product of the matrix with itself, which of course is that, taking the trace of AA transpose as it turns out. All right. Who cares? Right? Who cares? Well, what this means is that we have a notion of, how big a matrix is, right? What can you do once you have a notion of things being large or small? What can you do? What can you define? We can define if, let's say, A is a mapping from the natural numbers to let's deal with square matrices now. But I could do. I'm gonna focus on square matrices going forward. But much of what I'm saying would still be true for rectangular matrices. But let's talk about square matrices for a second here. So for a square matrix, if you have a function from the natural numbers to the matrices, what is that? What do you call a function from the natural numbers to some set? What is that? That is a sequence, correct. So we're looking at a sequence of matrices. What would it mean for this to have a limit?
It converges.
It converges, okay, great. The limit as n goes to infinity of, let's say, a sub n is equal to L if and only if what? If for what? For each epsilon greater than 0, there exists a big N in the natural numbers such that little n greater than or equal to big N implies that the norm of a sub n minus L is less than epsilon. So we can define the limit of a sequence of matrices once we have a notion of matrix length. That's why a norm is interesting, because it allows you to define sequences. And if you can define sequences, you can also define series, right? Likewise, if we were to talk about the sum, say k equals 0 to infinity of A sub k, where A sub k is a matrix, that would be understood to be the limit as n goes to infinity of the sequence of partial sums, which in this case would be k equals 0 to n of A sub k. All right? You can define a sequence being Cauchy in this context. So what's a Cauchy sequence? What does it mean for a sequence to be Cauchy? Some of you are in reals. Wait a minute, no, that's impossible. What am I talking about? So, so here's a look ahead to the real analysis sequence. Definition. A sequence A sub m is Cauchy sequence if for epsilon greater than 0 there exists, let's say, big N in the natural numbers for which m greater than n greater than big N implies that the norm of A sub m minus, big A. Big A sub m, I'll get it eventually, A sub m minus big A sub n is less than epsilon. This is the definition of a Cauchy sequence. What it's saying is that you can get far enough out in the sequence so that subsequent values in the tail of the sequence can't be more than epsilon apart. All right? So my question for you guys, let's take it back a step here. Let's think about what is a Cauchy sequence of, like, for example, a Cauchy sequence of rational numbers that I always tell students about, just to try to give you a little bit better idea about what Cauchy means. So let's just look at, what's a real number? 1 by 1 matrix example, right? It's kind of dumb. So how about this? A sub n defined as, how about this? A1 is 3, A2, 3.1, A3, 3.14, A4, 3.14, what comes next? 1, all right. A5, 3.1415, all right. Question, is every one of those values a rational number? Yes, they're all in the rational numbers. What, on the other hand, is the limit of this sequence? What does A sub n go to as n goes to infinity here?
Pi.
What's that?
Pi.
It goes to pi. Is pi a rational number? The answer is no. Pi is not a rational number. Don't ask me to prove that. All right? But we can prove that pi is not a rational number. So here we have a sequence of rational numbers. It's a Cauchy sequence, by the way. Can you see that this is a Cauchy sequence? As you go on out, the difference between two subsequent terms gets smaller and smaller and smaller. If you go far enough out, you can make the difference between the terms as small as you like. That's a Cauchy sequence. So this is a Cauchy sequence of rational numbers. But what's its limit? Its limit is a irrational number, pi, right? So the rational numbers don't have what's called the Cauchy criterion. The Cauchy criterion says that a Cauchy sequence must converge, right? So in the context of a rational sequence, Cauchy does not imply converge. Now you're like, but you just told me it converges to pi. Okay, context. It does not converge to a rational number. So in the universe of rational sequences, there are holes, right? We have sequences which we'd like to converge, and yet they don't, because we're missing something. We're missing the irrational numbers. So here's a definition for you guys. Definition: if every Cauchy sequence in V paired with a norm converges to a point inside V, then V paired with the norm is a complete space. It's a complete space. By the way, so you guys talked about inner product space is a vector space paired with an inner product, right? A vector space paired with a norm is called a normed linear space, or an NLS, or no, it's a normed linear space. If you have a normed linear space, which is also complete, this is what's called a Banach space. So. All right. What do you think? Are the n by n matrices a Banach space? Well, this is really a question for real analysis, truth be told. But in real analysis, you should prove, among other things, that the set of real numbers is complete. Cauchy implies converge in the real numbers. That rests on technical properties of the real numbers, what's called the least upper bound axiom, right? The fact that real numbers don't have holes essentially supplies the proof of that claim. But it is true, if you have like a real vector space with a norm like this, it is a complete space, all right? Essentially the real numbers, the completeness of the real numbers bequeaths the completeness of this space here. So what that means is if we have a sequence of matrices and we can show it's a Cauchy sequence, then that suffices to prove it converges. All right, so let me define something. Definition. E to the A is by definition the sum. Here we go. K equals 0 to infinity of 1 over k factorial a to the power k. All right. Do you guys know what this is called? If A is a matrix, what do you think this is? Mathematicians are very inventive with names. This is the matrix exponential. So there you go. We can prove that the matrix exponential converges by proving that it's a sequence of partial sums is Cauchy. So what's the sequence of partial sums look like here? So if I look at like, excuse me, S sub n, I've got the sum k equals 0 to n of 1 over k factorial a to the power k. And if I look at Sm minus Sm, my bad, Sm as in mommy, n as in nenu nenu, what does it leave you with? What happens if you know, I'm assuming m is greater than n. What are you left with here? There's a cancellation, right? K equals n to m? N plus 1, what do you guys think? Help a Jeff out. N plus 1, what do you guys think? Yeah, I think n plus 1. It's going to be kind of immaterial for the sort of arguments that follow here, but yeah. All right. So, some other fun facts, and you can work this out. The norm of A times B, if they're square, we can work this out. This is like an identity, which is true. It's actually less than or equal to the norm of A times the norm of B. So There's an analog of like the Cauchy-Schwarz inequality for dot products, but this is for the matrix product. So that's true. And if that's true, you can pretty easily see that this says, like, for example, the norm of a squared is less than or equal to the norm of a squared. English doesn't do it justice, does it? You gotta look at the board, you know? And if you can do it twice, you can do it k times. So like, similarly, and of course we could do induction to make this all nice and proper and such, but less than or equal to the norm of a to the k power. This is an estimate, which is true. There's another thing which I should mention, which is we've got our beloved triangle inequality. Like the norm of a plus b is less than or equal to the norm of a plus the norm of b. This can also be proved for the inner product that I started with today. By the way, this inner product that we're working with today for matrices is known as the norm is known as the Frobenius norm. Excuse me, Frobenius. Did you guys know who Frobenius was? Anybody? Yeah, me neither. I'm not that old. Dude's been dead a while. But he was one of the first people to write like a legit linear algebra book in n dimensions. Like the great 19th century mathematicians, they did stuff kind of here and there for like 2 dimensions or 4 dimensions or something. As I understand it, Frobenius came along and he wrote the first like genuinely like n-dimensional treatment of everything. So Frobenius maybe was the first guy to do a lot of these things carefully. And the theorems that are named after Frobenius are usually pretty formidable. There's a Frobenius theorem in differential equations. The Frobenius method in differential equations is, I don't use this term loosely, but it is beastly. I mean, it is. I've lost days to that thing. There's a Frobenius theorem in manifold theory, which concerns the possibility of like straightening out a manifold in a certain way. There's a number of different Frobenius theorems. Every last one of them that I know of is technical and deep. So anyway, all right. So now we have these properties. Take the norm of the partial, the difference of this. What do you got? The norm of Sm minus Sn is equal to the norm of this sum, right? But I'm going to use the triangle inequality to save myself some writing. See, I can trade that for the sum k equals n plus 1 to m of, and I can pull constants out of a norm too, by the way. So 1 over k factorial, and then I've got norm of a, and I'm going to go ahead and pull the k out too while I'm at it, because all of the inequalities are working in the right direction for that, right? But if you tilt your head and squint, you can see that that's actually the absolute value of Sm minus Sn, where Sm, well, let's say Sn is equal to the sum k equals 0 to n of the norm of a to the k power divided by k factorial. What happens as n goes to infinity for that? What's this go to as n goes to infinity? You guys have had calculus too. You know these things.
0.
Not 0, no. Something more interesting. In fact, it cannot be 0. It has to be positive.
Does that exponential necessarily grow faster than the factorial?
What exponential? Oh, you mean the power function? I really wish you'd just said that that's an exponential. That's what I was looking for. So this goes to e to the norm of a. This is straight up the power series for the exponential of the norm of a. Well, it's the nth partial sum in the power series. So as n goes to infinity, this goes to the exponential. Which means that if this goes to 0, it's a convergence sequence. Therefore, Cauchy And if this sequence is Cauchy, it means that this is Cauchy, which means that that is Cauchy, which then means that my series converges. What's the condition on the matrix? N by n. Yeah, was there, what is the condition though? Like, is there any condition? There's no condition whatsoever. My point to you is that the matrix exponential converges for any square matrix. This is something we can do to a matrix. Why do we care about this? Besides, like, you know, confusing the students with analysis that you haven't taken yet. All right, so why do we care? How many of you are in differential equations? Anybody? I see one. So, in differential equations, we learn how to solve systems of differential equations with constant coefficients. And maybe you guys saw that in your 221 course. I don't know. It's definitely inlay. It may or may not have been covered. Excuse me. Goodness gracious. Oh, thank you. I appreciate that. So, if we have dx1 dt is like a11 x1, a1n xn, and so forth and so on. Suppose you got n differential equations, first order, and these coefficient functions are all constant. So a1 through a(n), they're all constant. So you can trade this for dx dt equals to ax. So this is n first order differential equations. How do you solve this? Well, if you know eigenvectors and eigenvalues, you can write down a bunch of solutions from eigenvectors and eigenvalues. All right? So that's one thing you can do. But there's something really beautiful here in terms of the matrix exponential, which I'll show you guys. So what happens if you differentiate the matrix exponential? So let's take not just any a, but the a which is the matrix for this differential equation. What happens if we differentiate e to the ta? So I'll write it out. So this is I plus ta plus 1/2 t squared a squared 1 over 3 factorial t cubed a cubed plus dot 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 dot. If I differentiate that, you just do exactly what you think. You differentiate term by term. The proof of these things rests on the Frobenius norm that I was just talking about, detailed arguments from there. Analogous to arguments that you should have seen in Calculus 2, but no one in their right mind would cover with today's students. So ta squared plus 1/2. And I'm not saying my day's students was so much greater either. It's been a while since we had students who could really hang with what the material demands. Anyway, so that's what happens. And if you look at that, you can factor an a out. And what you got? You got the identity plus t times a, 1/2 t squared a squared. Well, it's the matrix exponential again. Yeah?
I'm sorry, I'm like a little bit behind. Can you explain what that says, n first order?
Differential equations.
What's the f? It's after the d, q.
Equations. Differential equations.
Oh.
It's okay. So this is a e to the ta. But yeah, you guys can jump in and ask me questions. It's cool. So the derivative of the matrix exponential is a times the matrix exponential. Sweet. What that also means is this is a matrix equation, but you can read it column by column. You can read this equation column by column. So like if you were to call this You know, if you were to talk about the columns of the matrix exponential, every column of the matrix exponential, when differentiated, gives you back a times the column. So what this means is that each column in e to the ta solves dx dt equals to ax. Now in differential equations, you learn theory about how to solve differential equations. And what you learn is that the nth order problem, it has actually a vector space structure. The nth order problem comes with a n-dimensional solution space. So even though the set of all possible functions is very much an infinite dimensional vector space problem, for a given differential equation, we find a finite dimensional context because the solution set theorems say that there exists a fundamental solution set consisting of n linearly independent vectors, functions. And so you're back into like the context of 321, you know, which is really cool. So what we're looking for to solve dx dt equals to ax is actually n linearly independent solutions. I would argue e to the ta has all of that, because I can prove to you that the columns of e to the ta are linearly independent. How would you do that? So think about this. E to the ta is n by n matrix. So here's my question for you guys. How to verify columns linearly independent? He did ask me to lecture on differential geometry today, but I just couldn't do it. I'm sorry, guys. Like I can't figure out how to lecture an hour on like differential geometry. It requires like 10 hours background. These things are not far from what you guys have been talking about. Differential geometry. Anyway, you guys have any answers for me? How do you check the columns of a matrix are linearly independent? It's a square matrix. Determinant. Very good. We could see that the determinant of e to the ta is non-zero. How about this? Does e to the ta inverse exist? If its inverse exists, we're good. How do you calculate the determinant of a matrix defined by an infinite power series? Well, the answer is you look up an identity. This is equal to the exponential of the trace of ta. And as such, it's positive. And also the inverse of this is e to the minus ta. So there's that. Whichever way you want to look at it. But guys, I should warn you, if we do e to the a times e to the b, and you study this, what do you guys think is going to happen? What's e to the a times e to the b? Where a and b are matrices. How's this work out? Guess, right? You can guess. What's the start of it? E to the what? E to the a plus b. And that would be exactly correct if a and b commuted, right? This would be it. This is actually true. If ab is equal to ba, that's actually the end of the story. But if a and b do not commute, it is not the case. If a and b do not commute, something more technical happens, of which I can only tell you the start. But here's what happens. And then I don't remember the sign, so I got to write plus or minus. There is a specific sign here, I just don't remember it. Guess what's in the plus dot dot dot? Oh, you're like, what is this thing you just wrote anyway? This means a commutator b is equal to ab minus ba. This is the so-called commutator bracket. It measures the fall from commutivity of two matrices. If that's 0, the matrices commute. So the higher order terms I haven't written there are actually nested commutators of commutators of commutators, and then worse, it's an infinite series of higher and higher nested commutators. This is known as the Baker-Campbell-Hausdorff relation. I'll just abbreviate it, BCH relation. This is important to physicists because this is what links the Lie algebra to the Lie group. All right, anyway, so my point is we actually do have, check this out though. So like TA and minus TA, do these commute? Think about it. Does a matrix commute with itself? What about a scalar multiple of the matrix? I mean, it does, right? Like a matrix commutes with itself. So actually, we don't have to do all this highfalutin mumbo jumbo. We can just do e to the TA times e to the minus TA is equal to e to the TA minus TA, also known as e to the 0. What is e to the 0 matrix? Yeah, exactly. It's just I, because everything here except for the 0th order vanishes. So it is exactly the identity matrix. E to the 0 matrix is the identity matrix. And that proves, as I claimed, that the inverse of the matrix exponential is just the matrix exponential with a minus. So matrix exponential is really nice, but it's also kind of formidable. It leaves us with this question, how on earth do you actually calculate this thing? Let me show you. So there's something beautiful that I like to call the magic formula. Here's the magic formula. It says this: e to the TA is equal to e to the lambda t times I plus t times a minus lambda I plus t squared over 2 a minus lambda I squared plus t cubed over 3 factorial a minus lambda I cubed plus dot 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 dot. Now you might wonder, where does this magic formula come from? The answer is a short calculation. Let me do it. So this identity I wrote is true for any real or complex scalar lambda. All right, I'm thinking of A as a real matrix, but lambda could be real, it could be complex. Either way, that calculation is legit. And so then what? But see, I mean, so this identity can be written for any real number, but it only is interesting. This is only interesting if we think about lambda being an eigenvalue of A. If lambda is an eigenvalue of A, really cool stuff happens with this formula. But anyway, why is that formula true? Check it out. E to the TA, use your imagination, is e to the t a minus lambda I plus lambda it. But lambda it commutes with everything, so I can rewrite this as e to the lambda it times e to the t times a minus lambda I. Now e to the lambda it is just equal to e to the lambda t times the identity matrix. But this busts out into the series that you see over there. That's that. So it's just adding 0. Do you guys remember eigenvectors? I know you studied them 221, but it's been a minute, right? You guys define for me eigenvector with eigenvalue lambda for A. What's it do? AU equals to what? Lambda U. You're right. You're like, you write your lambdas backwards. What's wrong with you? It's programmed. It's like it's I can't fix it. I've been doing it since like I was a teenager. I can't undo it now. I understand, technically speaking, this should be like that, right? That's the real lambda. Now you've seen it. Sorry. But anyway, font choices aside, a minus lambda I u is equal to 0 for an eigenvector with eigenvalue lambda. What happens when we take the magic formula and hit it upside the head with an eigenvector with eigenvalue lambda. Excuse me. What happens when you put u and multiply it into this infinite series of powers of the matrix A minus lambda I? What happens? Yeah, that's right. That's right. So this is 0, that's 0, that's 0. That's the only thing that survives is that first one. So we get e to the lambda t times u. This is known as the eigensolution of dx dt equals to at. It is the solution which is constructed simply by an eigenvector. All right? You'll find these in lay. All right? Why does that work? Why does this make sense? What is U times a matrix? It is a linear combination of the matrices, columns, right? Every column of the matrix is a solution to the differential equation. You're taking a linear combination of solutions to a linear differential equation, which means that you still got a solution. Not only that, there's a straight up formula for it. So we've gone from this infinite matrix, sum of matrix powers, which is kind of formidable, to something that's actually quite calculable, if you will. So then what? What's past this? What's past this is something called the Jordan form. Do you guys know what the Jordan form is? No. Not surprising, because it should be at the end of the course you're currently taking, if anywhere. Or if a crazy professor was teaching 221, he might do it at the end. Probably not me, though. Okay, that's a lie. I'm doing it. But, but I won't make them prove anything about it. I'll just help them find it. Show them what it does. That's 221 in my estimation. So here's the deal. If we have a minus lambda I times, let's say, uk is equal to uk minus 1 for k equals to, let us say, 2, 3, 4, all the way out to, oh man, let me put an n there instead of a k. I don't want to use n either. Dang it. J. So for j equals to 2, all the way out to k. And let's suppose that a minus lambda I u1 equals to 0. Then, excuse me, u1, u2, uk is k-chain with eigenvalue lambda. If you look at the basis that's formed by such a thing, all right? So if we call this thing beta, and we were to look at, like, suppose A itself is k by k. So if we look at, like, beta inverse A beta, what you get is lambda, 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 with ones on the super diagonal, zeros everywhere else. This is called the k by k. This is the k Jordan block. K Jordan block. It turns out that while a matrix cannot generally be diagonalized, right? You guys, when can a matrix be diagonalized? When is it possible to diagonalize a linear operator? Do you guys know? Oh no. The zero matrix is diagonalized. A little bit, but no. Here's the theorem. T is diagonalizable if and only if there exists eigenbasis for T. That's the theorem. A linear transformation from V to V, an endomorphism, is diagonalizable if and only if there exists an eigenbasis. So if T was diagonalizable, we don't have any need of the Jordan chains. Eigenvectors are more than enough. We can use the eigensolution to solve the problem. If A is diagonalizable, we can solve dx dt equals to ax just with eigensolutions, because we've got n of them. But if A is not diagonalizable, then you have to think about these things called Jordan chains. All right, so so like this condition here is the chain condition. Excuse me. And let me tell you what it means. It implies, for instance, that A minus lambda I squared on U2 equals to what? A minus lambda I cubed on U3 equals to what?
U1 and U2.
No. If there was just one there, it'd be U1 and U2, but there's a 2 and a 3. I have 2 powers, not just one. By assumption, this would be A minus lambda I U1, like you just said. But what's A minus lambda I times U1? By assumption, 0. And this, likewise, will be 0. So like Uj is generalized eigenvector with eigenvalue lambda for A. What that means is that the jth power of A minus lambda I, when it hits it, it gives you 0. However, the j minus 1th power is non-zero. That makes it a generalized eigenvector of order j. Order 1 is just plain old eigenvector. Do you see why those are interesting? Look at the magic formula. What happens with the chain condition? For example, let's do U3. What's e to the ta times U3? And I'll stop there. You guys have suffered enough. So e to the lambda t. See what happens when I hit U3 in through here? I get I times U3, which is U3. What happens? U3 times A minus lambda I gives me U2 plus T times U2. And if you work it out, you get 1/2 T squared times U1. Now that is something that you can't get from the eigenvectors. So the generalized eigenvectors end up giving you solutions to the differential equation which involve exponentials times time or time squared if there happens to be repeated eigenvalues. By the way, the eigenvalues are down the diagonal. So this is a repeated eigenvalue of lambda k-fold times. There's a theorem, we can work this out, that over the complex numbers there exists a Jordan basis for any matrix. Jordan basis is a concatenation of k-chains of different values for different eigenvalues. And when you look at the matrix and you similarity transform according to the Jordan basis, you get what's called the Jordan form, which is the next best thing to diagonalized matrix. So if you guys go to grad school, this will become important when you take linear algebra, or if you just any class that applies linear algebra. Stuff's important. So anyway, thanks.